Based on information from the National Electrical Code, there are specific requirements regarding neutral switching in automatic transfer switch applications, particularly in emergency power systems. The requirement to switch the neutral conductor depends on several factors, including the type of system grounding, the characteristics of the load being served, and specific code interpretations. In a 480-volt, 100-amp, three-phase system with an automatic transfer switch used to switch between a utility supply and an emergency generator, the first thing you need to know is whether the neutral conductor needs to be switched by the automatic transfer switch. Here's a breakdown of the factors to consider and the relevant code sections. The National Electrical Code Section 700.5 addresses transfer equipment, and it states that transfer equipment must be suitable for the intended use and designed and installed so as to prevent the inadvertent interconnection of normal and emergency sources of supply in any operation of the transfer equipment. However, this section alone does not explicitly mandate neutral switching. Now, to determine whether the neutral needs to be switched, it is crucial to understand the grounding configuration of both the normal source, which is the utility supply, and the emergency source, which is the generator. Here are a few common scenarios. Firstly, separately derived systems. If the generator is considered a separately derived system, which means it has its own grounding electrode system independent of the utility supply, the neutral conductor is generally required to be switched. The reason for this requirement is to prevent objectionable current from flowing in the grounding conductors. Objectionable current can occur when the neutral is not switched, creating parallel paths for neutral current to flow through the grounding system back to the source. This is addressed in NEC Section 250.6, which discusses the elimination of objectionable current. Secondly, solid neutral systems. In a solidly grounded system, the neutral is connected to ground at the source. If both the utility and the generator are solidly grounded and the neutral is not switched, it creates a parallel neutral path. This can lead to circulating currents and potential issues with ground fault protection. Thirdly, impedance-grounded systems. In impedance-grounded systems, the neutral is grounded through an impedance, typically a resistor. This limits the ground fault current to a specific value. The need to switch the neutral in impedance-grounded systems depends on the specific design and the potential for objectionable current. One of the primary reasons for switching the neutral in separately derived systems is to avoid circulating currents. When the generator neutral is bonded to ground, and the utility neutral is also bonded to ground, a parallel path is created for neutral current. This parallel path includes the grounding conductors and any metallic paths between the two sources. The current flowing through these unintended paths can cause several problems, including, firstly, electromagnetic interference or EMI. Circulating current in the grounding system can induce noise in nearby electronic equipment, leading to malfunctions or inaccurate readings. Secondly, voltage drops. Parallel neutral paths can cause voltage drops in the grounding conductors, affecting the performance of sensitive electronic equipment. Thirdly, nuisance tripping. Circulating currents can cause ground fault circuit interrupters GFCIs and ground fault protection GFB devices to trip unnecessarily. Fourthly, overheating. Excessive current in the grounding conductors can cause them to overheat, posing a fire hazard. The decision to switch the neutral should also take into account the type of load being served by the generator. Nonlinear loads, such as electronic equipment and LED lighting, produce harmonic currents. These harmonic currents, particularly the third harmonic, can cause increased current in the neutral conductor. If the neutral is not switched, these harmonic currents can circulate through the grounding system, exacerbating the problems associated with objectionable current. NEC Section 220.61 addresses the size of the neutral conductor for household ranges and electric dryers, and it provides guidance on how to calculate the neutral load based on the type of appliances being served. While the section is specific to dwelling units, the principles can be applied to other types of loads as well. The presence of nonlinear load should prompt a careful evaluation of the need for neutral switching. When the automatic transfer switch switches the neutral, it ensures that the generator neutral is isolated from the utility neutral when the generator is providing power. This prevents the circulating currents and eliminates the potential for objectionable current in the grounding system. The switch should be rated for the full load current and designed to withstand the available fault current at the point of installation. It is also important to ensure that the neutral switch is properly coordinated with the other poles of the transfer switch to prevent any transient overvoltages or imbalances. There are situations where neutral switching is not required or even recommended. If the generator and the utility source are part of the same service, meaning they share the same grounding electrode system, neutral switching may not be necessary. In this case, the neutral is already bonded to ground at a single point, and there is no potential for objectionable current. However, these configurations are less common in facilities with emergency generators, as the generator is typically installed as a separately derived system to ensure reliable backup power. The National Electrical Code provides guidance on grounding and bonding requirements to ensure electrical safety and prevent hazards. The primary goal of grounding is to provide a low impedance path for fault current to return to the source, allowing overcurrent protective devices to operate and clear the fault. Bonding, on the other hand, connects all non-current carrying metal parts together to create an equipotential plane, minimizing the potential for electric shock. NEC Section 250.4 outlines the general requirements for grounding and bonding, emphasizing the need to create a safe and effective ground fault current path. The specific requirements for grounding separately derived systems are found in NEC Section 250.30. This section details the methods for grounding the neutral conductor of a separately derived system, including the use of a grounding electrode conductor connected to a grounding electrode. The size of the grounding electrode conductor is determined by NEC Table 250.66, which is based on the size of the ungrounded conductors. The grounding electrode can be a metal underground water pipe, a metal frame of the building or structure, or a concrete encased electrode, among others. The requirements for bonding are covered in NEC Section 250.92, which specifies the methods for bonding metal enclosures, raceways, and other non-current carrying metal parts. The bonding jumpers must be sized according to NEC Table 250.102, which is based on the size of the circuit conductors. Effective bonding ensures that all metal parts are at the same potential, reducing the risk of electric shock. When dealing with automatic transfer switches and generator systems, it is essential to consider the impact of neutral switching on the ground fault protection system. Ground fault protection is designed to detect and interrupt low-level ground faults that may not be detected by standard overcurrent protective devices. If the neutral is not switched and circulating currents are present in the grounding system, it can interfere with the operation of the ground fault protection, leading to nuisance tripping or failure to detect a legitimate ground fault. The installation of ground fault protection is governed by NEC Section 230.95, which requires ground fault protection for solidly grounded wire services of more than 150 volts to ground, but not exceeding 1000 volts phase-to-phase for each service disconnect rated 1000 amps or more. This requirement is intended to reduce the risk of arcing faults, which can cause significant damage and pose a fire hazard. When installing an automatic transfer switch, it is important to verify that the switch is listed and labeled for the intended use. The listing ensures that the switch has been tested and certified by a recognized testing laboratory such as UL or ETL and meets the applicable safety standards. The labeling provides information about the switch's voltage and current ratings, as well as any special instructions or limitations. NEC Section 110.3 requires that equipment be installed and used in accordance with its listing and labeling. This means that the automatic transfer switch must be installed in a manner that complies with the manufacturer's instructions and the requirements of the listing. Failure to follow these instructions can void the warranty and potentially create a safety hazard. The specific requirements for automatic transfer switches are covered in UL 1008, which is the standard for transfer switch equipment. This standard specifies the testing and performance criteria for automatic transfer switches, including requirements for voltage withstand, current carrying capacity, and switching performance. When selecting an automatic transfer switch, it is important to choose one that is UL 1008 listed to ensure that it meets the necessary safety and performance requirements. In addition to the National Electrical Code and UL standards, local codes and regulations may also impact the requirements for neutral switching in automatic transfer switch applications. Local codes may have additional requirements or interpretations that are specific to the jurisdiction. It is important to consult with the local electrical inspector or authority having jurisdiction (OJ) to ensure compliance with all applicable codes and regulations. The AHJ has the final say in interpreting and enforcing the electrical code, and their guidance is essential for ensuring a safer and compliant installation. In conclusion, the decision to switch the neutral in a 480-volt, 100-amp three-phase automatic transfer switch application depends on several factors, including the grounding configuration of the system, the type of load being served, and the applicable codes and regulations. In general, if the generator is a separately derived system, the neutral is typically required to be switched to prevent objectionable current in the grounding system. However, it is important to consult with a qualified electrical engineer or the local AHJ to determine the specific requirements for the installation. Understanding the principles of grounding and bonding, as well as the requirements of the National Electrical Code and UL standards, is essential for ensuring a safe and compliant installation.